Hello and welcome to the invited talk and follow-up panel discussion on synergy among monitoring systems to address hazard mitigation and global challenges. I am Georgios Charalambous, and together with my co-convener Peter Nielsen, we are pleased to introduce Ms. Loretta Girardet, who will open this session with a presentation titled Welcome to Risk, as we know it, or do we? A few words about the presenter. Ms. Girardet is the Chief of Risk Knowledge Monitoring and Capacity Development Branch at the United Nations Office for Disaster Risk Reduction. This branch is covering risk information and analytics, climate change, disaster loss and monitoring data, and capacity building for UNDRR globally. Previously, she served as Chief of the Asia Pacific Regional Office, covering 38 of the world's most disaster-prone countries. Loretta served in various management positions at the Office for the Coordination of Humanitarian Affairs for over a decade before joining UNDRR, including overseeing the Global Cluster Coordination Mechanism, having responsibility for interagency standing committee mechanisms on coordinated humanitarian needs assessments. She also has a background in public health and worked for the World Health Organization in various capacities, including in emergency context in Afghanistan, Pakistan, and Sub-Saharan Africa. Her experience in emergency context spans more than 25 years, and she is the author of several publications, including Lifeline Media, Reaching Populations in Crisis, which promotes greater accountability to people affected by disasters. Her academic background includes fellowships and degrees from the Harvard School of Public Health and University of Paris. It is our great pleasure to have you, Loretta, with us. The stage is yours.
Thank you so much. And what a pleasure it is to be here to talk to you about our favorite subject, which is risk, from the United Nations Office of Disaster Risk Reduction. So I would like to share with you a presentation, hoping that, yes, it seems to be okay. Can you see it? No. Okay, so it's not okay. Let me go back then and see if I can get my screen. Hold on. Apologies. We've just tested this and it worked. Now it isn't. Okay. Try again.
Okay. Yeah, we have it.
Have it, but not the full screen, I think, right?
Not the full screen and not the first slide, I think.
Okay, I try.
So I think if you move up the presentation and click the first one and full screen.
Where is it?
Yeah, a little bit to the right. Again. One more there.
Sorry about that.
Ready to go.
Good. Thank you all so much to be listening today to the presentation on Welcome to Risk, as we know it, or do we? So I'd like to start off by reminding everyone a bit about the Sendai framework for disaster risk reduction. You probably are aware that the Sendai framework for disaster risk reduction really tried to lead to a paradigm shift, is trying to lead to a paradigm shift from managing disasters to managing disaster risk. And I think what's unique about the Sendai framework's approach to risk reduction is that it is really seeking to go beyond natural disasters and look at the broad range of risks that countries face. So here I've just highlighted the small scale and large scale, frequent and infrequent, and sudden and slow onset disasters. Let me just pause there for a moment why this is so important. Although much of the world's attention focuses on the disasters that stem from large-scale risks, such as an earthquake or tsunami, the reality is that what we are seeing, largely due to climate change, is an increase in small-scale, high-frequency, local-level disasters, which isn't really drawing the same level of attention. Yet the repercussions are especially grave in communities that are seeking to build, their economic development. So really a need for us to look at both small scale and large scale. And of course, the important element is that it's not just natural or man-made hazards that we're concerned with, but also environmental, technological, and biological hazards and risks. Now, our understanding of risk is also changing. And over the years, it was quite normal context to look at risk assessments that were carried out hazard by hazard. We would be assessing the risk of a flood. We would be assessing the risk of other types of hazards. Looking at risk in quite a compartmentalized way. Understanding risk today is very much about pushing back against reductive measures that ignore the systemic nature of risk or that treat risks in isolation of their context. So we're really aiming to look to break away really from the prevailing practice of compartmentalized research, hazard by hazard risk assessment and management, to try to find ways to improve our understanding of the rather complex systems and to identify solutions to manage systemic risk. And what, of course, we see is that when it comes to risk management, we are very compartmentalized and siloed. And this is a real challenge for the future. Of course, data and analytics also tend to compartmentalize risk and making it seem as if it's easily quantifiable when we know that that's not really the case. And if we just think about climate change, for example, due to global warming that's contributing to environmental degradation and biodiversity loss, with impacts on food production, international trade, financial markets, we really can see that risk needs to be understood in a much broader way. And here on this slide, we have the example of how risk can multiply, cascade, and ultimately lead to multiple systemic failures. So the next slide is, of course, the question of climate change. And I really highlight this because how we carry out risk reduction is changing and needs to change in the context of climate change. We are seeing that decades-old projections about climate change have come true much sooner than we expected and at a scale that we have also unfortunately predicted and is now coming true. The threshold of global warming increased to 1.5 degrees above pre-industrial levels have sought to cap will be surpassed by the early 2040s. And many of our risk reduction strategies and approaches, as far as we can tell, have not really yet taken into account the full scale and the full impact of climate change. So one of the pieces of work that we think is extremely important moving forward is to really look at how do you bring together the work around climate change, the science around climate change, and the actual work going on in countries around disaster risk reduction. I think we also need to look at what COVID-19 has meant and continues to mean for risk reduction and our understanding of risk. This for us is a very good example of systemic risk, where what was essentially seen as a risk in one sector, the health sector, has cascaded and had lasting impacts across multiple sectors. Very few countries were really prepared to manage the impact of this biological hazard across sectors such as transport or education or many of the other ones, food systems that have been impacted by it. So it's a real stark reminder of our need to branch out in how we manage disaster risk and how much more multi-sectoral approaches are needed than currently exist. So I'd like to talk to you a few minutes about how UNDRR is trying to strengthen global understanding of risk, but also change how we manage risk. And I wanted to maybe just focus on three areas here. We have identified for the organization as one of our key accelerators that's needed to achieve the Sendai framework, which I think is probably not a surprise to any of you, is not on target, in much the same way that the Sendai frame, as the Sustainable Development Goals are also not on target. And we need to really step up and accelerate our efforts to help countries get on target and to achieve the goal and objectives of the Sendai framework. So some of the areas of work we're really concentrating our efforts is first and foremost on strengthening risk information and evidence through an enhanced science agenda, through supporting comprehensive systemic risk assessments at the country level, improving disaster loss accounting, and monitoring progress in DRR. And I will talk a little bit more about some of this. But this other very critical point for us is really trying to promote far more comprehensive approaches to managing climate change as well as disaster risk reduction, in particular, climate change adaptation. We really see a need to risk-inform national adaptation planning, but also to look at how to strengthen the metrics for adaptation. And here we are in the process of building partnerships and alliances and promoting what we're calling comprehensive risk management, straddling both disaster and climate. And finally, we are seeing an absolute need to localize efforts around risk reduction. We have launched a partner prong approach called Making Cities Resilient, which aims to support local level resilience building. But this will include also systemic risk analytics tailored for urban settings, and looking again at how do we integrate climate change considerations into local urban planning. I'd like to share with you some of the work that we've done in the context of our planning that I've just mentioned. And one of them in particular has been quite an extensive piece of work around identifying what we see as the hazards that countries are facing. As I've mentioned to you, what's unique about the Sendai framework, or what has changed, if you want, in terms of the frameworks that we use to govern disaster risk reduction, moving from the Hyogo framework to the Sendai framework, has been this expansion in the hazards, not only natural hazards, but also taking into account technological, environmental, and biological. And with this in mind, through quite a consultative process with more than 500 scientists, UN agencies, and others, we have now identified 302 hazards to be addressed and managed at the country level. And these have been clustered into 8 different types of hazard clusters, including meteorological and hydrological hazards, extraterrestrial hazards, geohazards, environmental hazards, chemical, biological, technological, and societal hazards. And for the interest of this audience, perhaps you'd be interested to know that 5 of these are nuclear-related hazards. Now, the definition and classification review that we've undertaken will be going online, and it also includes several recommendations on how countries can use these hazard definitions to inform the type of risk reduction and other types of work that's needed at the country level to better manage these. Certainly, what we are seeing is a real need to investigate further the direct, but also the indirect linkages and effects of natural, biological, technological, and other human-induced hazards to better understand how they interconnect, how they cascade, and the complex nature of these various types of hazards. Having information about hazards and as well as vulnerability and exposure, that combination that makes up risk, is really not enough. What we really need to do and what we're focusing on is helping countries use risk information to inform decision-making, to inform development and humanitarian planning. So the other piece of work that we have launched is the Global Risk Assessment Framework. And the aim here is to help member states to better use risk information to inform their planning processes. It has 4 pillars, this initiative. And the first is to aggregate risk information in a manner that's usable by countries. Often we hear from countries that they do not have data on risk. In fact, they often do, but it's laying in different ministries or other entities, and it's not brought together, it's not aggregated. So this is a service that UNDR is providing to countries. But we also have brought together a group of about 100 or so risk experts from around the world that will be able to help countries carry out bespoke risk analytics around certain issues that they are facing. And other parts of this initiative include building capacity to better use risk information, but also expand the use of risk information beyond the usual suspects, which are the national disaster management or civil protection agencies. We really feel a need for planning ministries and finance ministries, for example, but others, the private sector as well, to be more risk informed and to have a better use of risk information. This is just an example of the type of data platform that we will be rolling out in countries. And just to let you know, some of the countries that are the first pilots include Eswatini, Costa Rica, Pakistan. So it's a mixture of humanitarian and development contexts. But the idea is to aggregate the best data available around this types of data sets that you see in front of us, and to help the countries make sense of the data so that they can draw conclusions and prioritize actions to reduce risks. Oops, what's happening? Sorry. Next slide. We are also looking to support better management of risks such as NATEC. And of course, you will all be aware of the 2011 nuclear accident in Fukushima in Japan that was caused by the Tohoku earthquake and tsunami, but had an impact in terms of the nuclear disaster. We call this NATEC. And here is an example of where the traditional approaches to risk management are really not sufficient, that the need to manage or to reduce the risks associated with possible NATEC disasters really require the engagement and partnership between various line ministries. And so this is a piece of work that we've carried out to really start socializing the ideas of NATEC risk management, and it includes the 10 principles that I've mentioned, that are mentioned here on the screen. Like, maybe just say a word about monitoring, because as we obviously work to help countries better manage risk, we are also looking to ensure that we are measuring the impact of this work, measuring our the successes that we are having in terms of implementing the targets and goals of the Sendai framework. And the point I wanted to make here is that we don't want to really see the Sendai framework in isolation of the larger picture, which is sustainable development. And so we have ensured that all of the targets of the Sendai framework are aligned to the Sustainable Development Goal, and that the monitoring systems are also feeding into the measurement of the Sendai development, the Sustainable Development Goals. The aim, of course, for us is risk-informed development at the end of the day. And so the targets that we have listed here in terms of decrease in mortality, the number of people affected, decrease in economic losses, but also an increase in the number of countries with national and local DRR strategies. These are very much aligned to the targets and goals of the SDGs. But it's not necessarily easy. We are seeing that the measurement of in terms of how well we're doing is quite challenged. Many of the countries that do have disaster loss databases in place are not necessarily using the data to inform the decisions that we would like to see. So there's not a direct correlation everywhere in terms of databases and managing databases and tracking losses and using that information to inform planning. We do see a need for a common statistical framework for disaster-related statistics across the UN. We see far better coordination is being required. The data is scattered in many different locations, and it becomes very challenging to make sense of it and use it for decision making. There is low statistical capacities in line ministries. And of course, the Sendai framework in itself is not binding. So it is really a question of working with countries to ensure that there is the will to collect the data and to use it. And right now we're seeing serious limitations in terms of sex, age, disability, and income disaggregated data. So far more work to do on the data front at the same time that we are building, we hope, the capacity of countries to identify and manage risks. So I'd like to maybe just conclude with some key messages around understanding risk. We really promote the idea that risk is systemic, interconnected, and cascading. If COVID wasn't an example of this, I don't know what is. That means we need to change the way that we manage and understand risk. And climate change in particular is creating this urgency for transformative adaptation and for better understanding of how climate change interacts with other types of risks. The days of one hazard, one impact are definitely over. We are seeing, and we have seen in many countries, dual and multiple disasters occurring at the same time. Think about a typhoon at the same time that COVID was taking place in the Pacific or in India or in Bangladesh, and the challenges that this caused. So we need to manage these disasters differently. Of course, the other big piece of work for us is that understanding risk is more than understanding hazards. There's still a tremendous amount of work to be done in better understanding of exposure and of vulnerability. And this is where we're placing quite a lot of emphasis with the GRAPH project. And finally, data is key to many of this. Interconnecting all of our knowledge is core. And this requires much better collaboration between many different partners who may not have previously seen themselves at the forefront of disaster risk reduction. So thank you very much. I leave it there.
Loretta, thank you very much for such an interesting presentation and for paving the way so nicely for the discussion. So as you are part also of the discussion that follows, we'll take questions at the end. And at this stage, I would like to present the moderator of the discussion, Professor Bruce Howe. He is a research professor at the University of Hawaii at Manoa, and he's the chair of the Joint Task Force for Smart Subsea Cables. SMART stands for Science, Monitoring, and Reliable Telecommunications. Bruce, after obtaining engineering and oceanography degrees at Stanford University and the University of California at San Diego, he worked at the APL Laboratory, University of Washington, and since 2008 at the University of Hawaii at Manoa, Department of Ocean and Resources Engineering. Currently, he develops ocean observing infrastructure from the provision of power, communications, and positioning throughout the ocean volume, with an emphasis on cabled and acoustic systems. As chair of the International Joint Task Force Smart Cable Initiative, Dr. Howe is leading the effort to incorporate sensors into commercial transocean submarine telecommunication cable systems to form a planetary scale observing system for climate, ocean circulation, and sea level monitoring and tsunami and earthquake warning. Past projects have included basin scale acoustic thermometry and planning, development, and operation of cable observatories. At Station Aloha, 100 kilometers north of Oahu, Dr. Howe and his team installed and operate the Aloha Cable Observatory, the world's deepest plug-and-play power and internet node on the planet at 4,728 meters water depth, now with 10 years of continuous data. Bruce, aloha, the stage is yours.
Thank you, Georgios. Let me try and get my screen working here. Good. Can you all see that?
Yes.
Okay, good. So yes, this is the panel on synergy among monitoring systems to address hazard mitigation and global challenges. This is just the brief outline of the next hour or so. First, I'll introduce the panelists, then session goals and questions, and I'll attempt to give a brief introduction to the CTBTO International Monitoring System to provide some background, and then each of the panelists will give a short presentation, and then there'll be a discussion based on a number of questions, and we'll entertain, if there's time, questions from the audience. So first, let me introduce panelists. First, Professor Dwi Korita Karnawati has been head of the Indonesia Agency for Meteorology, Climatology, and Geophysics, also known as BMKG, since November 2017. This is after serving as president of the Universitas Gajah Mada, a prominent university with 55,000 students in Indonesia. She has extensive professional and academic experience as a professor in environmental geology and disaster mitigation, and is very active in promoting and developing national multi-hazard early warning system. Obtaining the PhD in Earth Sciences from Leeds University in the UK in 1996, she continued her research on the prediction of hydrometeorological disaster through postdoctoral program at the Tokyo University of Agriculture and Technology in Japan in 1997. Afterwards, Professor Karnawati consistently worked on many capacity development and education programs for disaster mitigation since then. And she's worked extensively on community-based landslide early warning systems. In 2019, she was elected as chair of the Intergovernmental Coordination Group of Indian Ocean Tsunami Warning and Mitigation Systems. That's how I know her. In her recent position as head of the agency, she actively drives innovation on early warning technology and impact-based forecasting systems for meteorology, climatology, and geophysics. So, and then our next speaker, I'm not, she hasn't signed in yet to my knowledge, but Eslin Gerbiti is Director General of the Ministry of Climate Change, Change Adaptation, Meteorology, Geohazards, Environment, Energy, and Disaster Management in Vanuatu. And previous to this, she led the Vanuatu Geohazards Observatory and the Department of Meteorology and Geohazards. Next is Etienne Charpentier is head of the World Meteorological Organization Observing Networks and Measurement Division, coordinating implementation of the WMO and integrated global ocean observing system, and providing oversight on evaluation of WMO surface-based observing systems. He has extensive experience in international affairs on aspects related to the rolling review of requirements, implementation, and evolution of in situ observing programs, and related data collection and exchange, data management, and quality management. He's been with WMO since 2006 after providing coordination and support towards implementation of the in situ ocean observing networks contributing to WMO and the Intergovernmental Oceanographic Commission, IOC of UNESCO. He started his career at Météo France in 1986 after graduating from the National Meteorological and Engineering School in Toulouse. Next is Steele McFeely is head of statistics and information at UN CTAD Conference Trade and Development. He's also adjunct professor at the Center for Policy Studies at University College Cork in Ireland, and the director of IASC International Statistical Literacy Program. He's co-chairman of the Committee of the Chief Statisticians of the UN System, chairs a panel to the UN Development Panel Program Human Development Index, and he's elected member of the International Statistics Institute. He was co-lead on the data strategy of the Secretary General for Action by Everyone, Everywhere 2020 through 2022, and lead author of the 2020 System-Wide Roadmap for Innovating UN Data and Science. Before joining UNCTAD, Steve was the Deputy Director General of the Central Statistics Office in Ireland. And we congratulate him on taking up a new post now in July at World Health Organization as Director of Data and Analysis. And with Loretta will also be on the panel, and with Georgia introduced her earlier. So moving on here, just to review, thanks Georgios for organizing this. Wait a second, there. And just to review briefly, the goal of the session is to discuss existing or potential synergies between CTBT and international organizations and agencies to address global challenges, disaster risk prevention, and mitigation of natural hazards. An example of synergies are IMS data contribution to institutions in order to enhance their missions. And initially, as an example, CTBTO provided data to tsunami warning centers after 2004, and soon Chile will be receiving such data as well. And in recent years, the scope of this concept has broadened to include earthquake monitoring, volcano eruption monitoring for aviation, and maritime safety, underwater acoustic anomalies monitoring, and extreme weather events and phenomena, as well as detection of radioactive emissions and dispersion to warn and protect citizens. And the objectives of such monitoring systems are in line with global challenges and the goals outlined in the UN Sustainable Development Goals, the Paris Climate Agreement, and the Sendai Framework. So we'll be addressing those. So the main questions for the panel, and we'll get to these specifically in the discussion period, how to better achieve synergy, either for global challenges or specific hazard mitigation. And how could the CTBTO verification performance be improved by additional sensing capabilities at existing stations for simultaneously benefiting civil and science applications such as weather forecasting, measurement of temperature, and so on, improve sensitivity and reliability of the radionuclide stations, and disaster risk reduction parameters. Next, how to improve the synergy between the International Monitoring System, IMS, and other monitoring systems, and between CTBTO and other organizations. And lastly, how does CTBT IMS data support specific projects in both global challenges or disaster risk mitigation? So at this point, let me give a very brief overview of CTBT and the IMS, just to review and provide context for those of you not familiar with this. So the primary objective of the Comprehensive Nuclear Test Ban Treaty, CTBT, is outlawing nuclear test explosions in all environments. And this constitutes an effective measure of nuclear disarmament and non-proliferation in all its aspects. As next to climate, let's say, nuclear war is an existential threat to humanity. And so this is an attempt to mitigate that. The treaty was adopted by the UN in 1996, and a preparatory commission was set up and located in Vienna. And its task is to establish a global verification regime to monitor compliance with the treaty and to promote the ultimate signature and ratification of the treaty for entry into force. This shows a map of all the monitoring stations the international monitoring system consists of within CTBTO. And you can see they're spread out over the whole globe, and it consists of primary seismic sensors, auxiliary seismic sensors, radionuclide system stations, hydroacoustic stations in the ocean, and infrasound stations around the world as well. And there are 4 monitoring technologies, basically collecting waveforms, wave data of different types. So 50 primary, 120 auxiliary seismic stations, so looking at seismic waveforms, and then hydroacoustic stations looking at the acoustic waveforms in the ocean. And then similarly in the atmosphere, 60 infrasound stations. And then the radionuclide stations collect local samples of the atmosphere to decide whether there's traces of nuclear explosions, and also collect noble gas monitoring systems. So it's quite a comprehensive system, and the goals are immediate detection, time and location from the waveform data, and then the radionuclide data provides evidence after the fact with some time delay of fission products and so on. And this cartoon just shows these elements all working together: hydroacoustic in the ocean, seismic on land, infrastructure on land, and then the radionuclide also on land. And they're all transmitting data in real time back to the International Data Center in Vienna and elsewhere. So that gives a quick overview of what CTBT is doing in the way of international monitoring. So next will be the presentations by panelists, and I'll be the first panelist. So let me get that screen open here, and let's see. Just a second, I'm going to have to switch. Let's see here, just a second. I'm going to have to go back and forth here. And okay. So let me begin here. So greetings and aloha to everyone. I'm pleased to moderate this panel session. And here I'll be describing the Smart Cable Initiative and then indicate its role in global monitoring and how together with others we can better address global monitoring. SMART stands for Science, Monitoring, and Reliable Telecommunications. The vision of the Joint Task Force for Smart Subsea Cables is to observe the oceans and Earth with a planetary scale network of sensor-enabled submarine telecommunication cables, delivering tangible societal benefits. The Joint Task Force, or JTF, is sponsored by 3 UN agencies: the International Telecommunications Union, the World Meteorological Organization, WMO, and the UNESCO Intergovernmental Oceanographic Commission, IOC. About 190 JTF members from over 30 countries, representing 110 organizations, are volunteering their time and expertise to bring this smart cable concept to fruition. So this is a little busy. I'll spend a little time on this slide. So the mission is to implement this telecom plus sensing smart subsea cable system on a global scale to support climate, ocean circulation, sea level monitoring, and tsunami and earthquake early warning and disaster risk reduction. This will be a first order addition to the ocean and earth observing system. We will share the submarine telecommunication network that links countries and continents together, enabling our society and civilization. We'll leverage this amazing living real-time network, a $5 billion per year industry consisting of 1 million plus kilometers of cable, 20,000 repeaters every 70 kilometers or so that ultimately can host sensors, constantly being replenished with an engineering life of 25 years. Telecom is a primary mission with smart secondary. The smart portion shall not have any negative impact on the telecom portion. The basic sensors are bottom pressure, temperature, and seismic acceleration. By better knowing the cable environment, we can better assure cable integrity and the network. Oops, there, okay. And the orange circles represent first systems. A number of systems are in various stages of planning, requests for proposals, and implementation. One green circle represents the CAM system underway with smart capability in Portugal or in Portuguese waters. And the other green circle down near New Zealand and Antarctica represents a cable going from New Zealand to Antarctica. I just finished over the last few days a workshop sponsored by the U.S. National Science Foundation discussing such a possible cable. Again, the primary purpose is connectivity, in this case, to better enable science on Antarctica as well as along the cable itself. The Smart Cable program is innovative and transformative, a perfect example of the blue economy within the context of the UN Decade of Ocean Science for Sustainable Development. It can contribute to and complement the hydroacoustics and seismic components of the CTBTO International Monitoring System, with information from each helping the other, as well as other monitoring systems as well. So why are we doing this, creating a smart network? The major reason is because humanity's greatest existential threat, as I've said, is climate change, and smart cables can contribute. With smart real-time observations, we will contribute to the Sustainable Development Goals of the UN 2030 Agenda and the Sendai Framework for Disaster Risk Reduction. And these SDGs are integral to the UN Decade of Ocean Science. We will contribute to the knowledge of climate change, including ocean circulation, temperature changes, heat content, and regionally variable sea level rise, as well as mitigating the threats of tsunamis and earthquakes. At the same time, improving societal connectivity, the primary mission of the cables, through improved cable integrity with awareness of their environment and network resilience, using the knowledge of the environment from smart cables to better plan future cables. I should say also that the data from the systems will be able to help mitigate risk, disaster risk reduction by, for instance, better informing how to build infrastructure along coastlines. This is just a simple cartoon showing some of the components of the ocean and earth observing system. Satellites are crucial with complete global surface coverage. Smart cables will complement and augment other in situ elements such as Argo floats here, dart buoys for tsunamis, and hydroacoustic stations from CTBTO, providing for the first time comprehensive deep ocean sustained observations. Let's look at the projection of SMART onto the UN Decade of Ocean Science. By leveraging the robust global telecommunications network, we will be able to transform our ocean infrastructure, providing a new platform for observing the ocean complementing and filling in the huge observing gaps that we have and enabling improving modeling and prediction. Smart observations of ocean bottom temperature and pressure support monitoring of the ocean portion of the atmosphere, ocean, climate, Earth system. Smart cable measurements of ocean bottom pressure and seismic acceleration will directly contribute to early warning of earthquakes and tsunamis, saving lives and infrastructure, and to understanding sea level rise and thus inform mitigation of climate-related coastal flooding. Smart cables emphatically address Challenge 7, sustained ocean observing. Within the decade, we have the potential of having thousands of deep sea mini observatories delivering real-time quality control data to warning centers and all users. Think global, real-time, long life, reliable, sustained, maintained, expandable, and with data managed according to FAIR principles, findability, accessibility, interoperability, and readability. The CAM system off Portugal is a perfect example of a smart system at this point in the smart development. This system replaces an older system, and it will link the continent to the Azores and Madeira in a ring, explicitly smart system, with other sensing as well. A prime motivator is a very destructive 1755 earthquake and tsunami. The government will be bearing the cost, no citizen left behind, for territorial cohesion and disaster warning. The LEA group here mentioned is providing science advice to the implementing IP telecom. I might add that it took 2 years to come up with quantifying the effectiveness of such a system for early warning. And just recently, they've come out and completed a seismic study showing that just by providing seconds of early warning for an earthquake, they can basically pay for the entire system itself, not just the incremental cost, but the entire system. And this should be in place and working by 2024. So lastly, concluding, as well proven, transformative technology transforms science, in this case, enabling unique ocean observations of major importance with societal benefits. It will extend infrastructure into the ocean, powering communications, and unlock the deep ocean. With respect to this panel, each system, IMS, Smart, Goose, Global Ocean Observing System, and WMO Weather, can provide complementary context for others. Hydroacoustic and seismic data from SMART and IMS can improve performance of each mission via improved estimates of the propagation media. Similar data, for instance, ocean acoustic, can be used for multiple purposes: CTBTO purposes, tsunami warning, climate change via acoustic thermometry, and more. Modest adjustments within one system can provide more improvement for another, for instance, smart seismic sensors and local improved IMS hydrophone locations. Coordinated planning and future sensors and facilitate data flow. So I hope this has provided a view into the Smart Cable program and how it fits into exploiting synergies between it and other global monitoring systems to mutual benefit. So thank you. And with that, let's see, I'll stop sharing. And I'd like to invite Professor Karnawati to begin with her presentation, and we'll continue through the panelists. So, can we have Professor Karnawati take the screen, or
Yeah, we are sending you a request to unmute. So, have you received the request?
Yeah. Right. Okay. Thank you.
Okay, perfect. No worries.
Sorry. Thank you. Thank you very much for the invitation and for having this great opportunity to be together with others, to listen, to learn, and perhaps to share the information. Well, first of all, I'm Karnawati from Indonesia, the Agency for Meteorology, Climatology, and Geophysics of Indonesia. I would like to highlight the importance of being together with CTBTO for several important problem solving. Before talking about that, the first slide, I would like to let you know that we have signed oh, excuse me. Okay, this one first. Okay, we are in Indonesia. Indonesia is the region which is very complex in terms of geological and tectonical conditions, as well as in terms of the climate conditions. So we quite frequently strike by the occurrence of the earthquakes. So we can see that the position of Indonesia in between Australia and Asia, and we can see that we are part of the ring of fire, which have struck by thousands of earthquakes. Next slide, please. So this is the example, the earthquake epicenter with the red color. That means the shallow earthquake epicenter with the depth of about 40 kilometers or less. Of course, this can be destructive and dangerous for the life and for the environment. So that's why we do need to have continuous and very intensive earthquake monitoring. Next slide, please. So this is one reason why we need to join with the CTBTO is, of course, it's for the nuclear radiation or nuclear activity monitoring, but also we can use the system or the instrument that we got from CTBTO. We have 6 stations of CTBTO monitoring, and that, of course, very important to support the monitoring of the nuclear activity, but also for the earthquake activities. So what we did, we have signed to be the member of CTBTO in 1996. Then we conduct several activity, including hosting 6 auxiliary seismic stations and rectified. Our membership is rectified in 2012. Then we also have signed the tsunami warning arrangement in 2008, and Indonesia is also part of, apart from the ASEAN earthquake monitoring center. So Indonesia to become the ASEAN earthquake information center, and we also provide a tsunami service provider, and we also to be a national data center. And of course, we also take a role as the National Tsunami Warning Center. And when we work on earthquake monitoring, because the earthquake also probable to result in tsunami, that means earthquake monitoring also to be part of the tsunami early warning system. So the picture at the bottom showing or illustrating the place or the center where we provide earthquake monitoring and tsunami early warning, which was established in 2008. Next slide, please. In the next slide, I would like to let you know the position of the 6 stations that we have installed. Those in Sumatra, in Parapat, North Sumatra, then also in Lembang, West Java, in Sulawesi, also in East Nusa Tenggara, in Papua, and in Jayapura, in West Papua and in Papua. So it is across Indonesian territory. Additional CTBTO station outside the Indonesia, we also have the access to Izu Island in Japan, and also in Ogasawara, Japan, in Thailand, also in Mindanao, then in Australia, in Peru, in Solomon Island, as well as in Marianas Island, USA. And the next slide, I would like to show you that Indonesian NDC need or plan to add more CBT station to increase its capability for detecting an unusual seismic event. Unusual, like what happened just recently, that the tsunami, a seismic event, which not directly result in a catastrophic tsunami. So like Professor Bruce just presented, actually, for the tsunami and earthquake experts, nowadays we are facing with very challenging phenomena. That's the tsunami, which not always resulted from earthquake. So our detection somehow is not capable to monitor or to detect that in accurate and timely. So this is the reason why we need innovation in additional observation system. So that's why we are thinking, we are dreaming, perhaps by having additional CTBTO station or having the data access, not the station, but the data access from like what we show show you here. It's about 12 points, yeah, in Asia, and we can see from that picture, if we can integrating the data of CTBTO into our Indonesian earthquake and tsunami early warning, that will really helpful to improve the capability, the accuracy, the timely, the time accuracy for our early warning. So integrating CTBTO to our existing system again will be very important. The next slide, we can see here that from our station in 2017, from Indonesian station, which is in East Nusa Tenggara, we can also detect nuclear testing. So it means the system of CTBTO, which is installed in Indonesia, is quite important, meaningful for us as well to do several mitigation. Apart from that, the right graph showing how indication of the last Molucca tsunami earthquake in June 16th, just a couple weeks ago. It also can be detected from the CTBTO auxiliary stations. So it is a proven evidence that indeed the function of CTBTO monitoring is really meaningful for multi-purposes, not only for the earthquake, but also for hazard monitoring. And next slide, I would like to show you that in Indonesia, you can see from the dot, yeah, the red dot showing the position of submarine volcanoes. which are all active. And the activity of submarine volcanoes can be very dangerous, can be very catastrophic, not only due to the eruption, but also due to the catastrophic tsunami induced from the collapse of the eruption, like what has been occurred in Sunda Strait in 2018. It's about 3 years ago. We are struck by the submarine landslide induced by the volcanic activity. For that, now we have not yet a proper instrument to monitor that, even to provide early warning. So this is the reason why we consider if we have a submarine monitoring, hydrostatic monitoring can be provided from CTBTO station, this can be very meaningful to save thousands of the people life. So this is the idea to be proposed to CTBTO, that we need to have also detection, hydroacoustic and infrasound, that for supporting the multi-hazard event, to detect the multi-hazard that can be the submarine volcano activity, as well as the impact of that submarine activity, like the tsunami. And next slide, I would like to show you, yes, it is just the example how the earthquake and tsunami in Palu, that the occurrence is very quick, very fast. The tsunami, normally tsunami arrive in our place in Indonesia is about 20 minutes up to 30 minutes after the occurrence of the earthquake. So we have about 20 minutes golden time to save, to evacuate our people from the tsunami. So normally 20 up to 30 minutes. Unfortunately, this tsunami arrived in 2 minutes, not the 20 minutes. So that's why we could not successful to evacuate our people, because our early warning in that time takes 5 minutes from the earthquake occurrence. So if we calculate 5 minutes and then the tsunami arrived 20 minutes, so there's still golden time 15 minutes. So now 15 minutes is too late. We need 2 minutes. So that's why we need like a cable-based tsunami meter, like Professor Bruce mentioned in his presentation, but may also like the tsunami detector submarine, which can be installed by CTBTO, like hydroacoustic and infrasound, for instance. That not only occur in Palu, but also in Sunda Straits, we face a similar case. So next slide, I think the last slide next. The CTBTO is also very keen to provide technical training. It has been several times we participate in the technical training, and also we has been trained how to maintain the system installed in Indonesia. So luckily the system works very well because we can maintain properly like has been trained, and the training is very important. So that's why we also propose that we can have the second man in CBTO headquarters. It means like in WMO, every year we can have one of our staff to stay there, conducting several works with a colleague in CTBTO. So our staff can also have the learning process, knowledge transfer. Then we can bring back to Indonesia, and then the next year, the following year, there will be another person. We have done that with WMO for 5 years. So hopefully it can be done also with the CTBTO. And also we are dreaming can have the joint research or joint collaboration with the CTBTO, especially for identification or detection, early detection of natural as well as artificial phenomena to support CTBTO verification regime in our region, as well as to support the multi-hazard early warning. And also here, we propose, actually, we apologize that actually we plan to have to conduct or to host the training in 2020, but unfortunately to be canceled due to the pandemic. So we still expecting it can be done after the pandemic has ended. And finally, we would like to conclude that being the member of CTBTO, it is really important for us because we can have additional information, additional capacity to detect or to provide early warning. But then we do expect this existing benefit could be further improved by having more data exchange or joint observation, like we proposed in the previous slide, 12 sites or stations in Asia, the data exchange or joint observation. And finally, also we need to have further capacity development. It can be offline or it can be online. Thank you very much for your kind attention. Thank you.
Thank you, Professor Karnawati. Very nice. Good. Next is Eslin van Vanuatu online? I don't see her. Okay, let's move on to Etienne Charpentier in the World Meteorological Organization. You're next. Could you share your screen and begin? Let's see. Maybe you could unshare your screen, Farida. Top of your screen, there should be a orange red button.
Okay, so thank you, Bruce. I hope you can see my screen and hear me correctly. So thank you very much. So WMO, we are a specialized UN agency to look at the state and behavior of the atmosphere in relation also to its interaction with the ocean.
Etienne, can I kindly ask you to go to the full screen presentation so that we can see better?
I am actually using a full screen presentation, but maybe I'm not sharing the right screen. Yeah. So yes, I would have to stop sharing. Share again.
Okay.
Can you see better?
Yeah, very nice. And please speak up a little bit because the sound does not come as loud as it should. Thank you very much.
Yeah, thank you very much. Yeah, I was explaining that WMO is a UN specialized agency involved in cooperation and coordination of international activities to assess the state and behavior of the atmosphere and its interaction with other Earth system domains. So in doing that, of course, protecting life and property is a priority in WMO. And we have a number of disaster risk reduction related applications that WMO or its members are supporting. So we basically provide information to national authorities so that they are able at the end to make appropriate decisions. So that there is a range of applications where we contribute high impact weather, of course, tropical cyclones, storms, floods, heat waves and drought. Climate change, of course, is important in the WMO agenda. In relation to CTBTO, we have environmental emergency response. So we have a nuclear and non-nuclear ones. Tsunami monitoring and providing information on atmospheric composition, for example, in relation to health. Recently, so we have had our Congress a couple of years ago, and here we have adopted a new strategic plan and a so-called Earth system approach. So basically, what we want to do is to look at the planet as a whole, where the atmosphere is linked and is interacting with the ocean, hydrosphere, terrestrial domain, cryosphere, and biosphere. WMO has a long history in providing support to, for example, the World Weather Watch. So we have been doing that for nearly 70 years now. And we have built a stronger infrastructure for global numerical weather prediction. But over the years, we have improved our global NWP tools to introduce better interactions with the other system domains. So we have a good level of maturity to do that now. One thing that is critical here is that we gain access, increasing access to data, especially in other domains than the atmosphere. But of course, we still see gaps in the atmosphere. So as I said, the disaster risk reduction application, they rely on the products that are provided by models, and especially in the context of this system approach. In terms of data needs, so there are two aspects there. One is to fill the gaps where there is no infrastructure available. So we have to make sure that infrastructure can be deployed, and capacity development in that regard is essential. So we have introduced a new program, which is called the Global Basic Observing Network, and a new initiative, which is called the Systematic Observations Financing Facility, whereby WMO is collaborating with financing organizations in order to, at least for the least developed countries, to assist them to and find the financial resources to fill those gaps. But another way to fill the gaps is to look at the existing infrastructure and work with partner organizations and make sure that those data could be made available in real time and sometimes in delayed mode, because it can still be useful to address the needs of WMO. So for that, we have introduced we are introducing a new data policy, so-called unified data policy for the international exchange of system data. It was recently approved, well, recommended, I should say, by the Executive Council, and it will go to Congress for approval by the end of this year. So hopefully by then we will have a new instrument for promoting the exchange of data. In WMO, we rely heavily on infrastructure. So we have three systems here. So starting, to be able to provide the products and the information that the society needs, we have the so-called Global Data Processing and Forecasting System, GDPFS, which relies on data that are provided by the WIGOS, WMO Integrated Global Observing System. And of course, you need to be able to exchange data. So we have the WMO Information System for data exchange. And for that, we have developed over the years a number of technical regulations, standards, and best practices that WMO members have to follow. So this gives you an idea of the type of technology that we are using for global NWP system prediction and monitoring. So we look at satellites, of course, remote sensing with weather radar, wind profilers, We launch radio sounds. We make use of marine observations. Bruce has mentioned the Argo program for the deep ocean, for example, or surface buoys. So it's a very complex observing system. Nevertheless, if you look at the observations on land here, and some observations that you see are being reported from small islands, for example, there are still gaps. So the colors on the map here show you the gaps in terms of data availability. So you see where stations are, but in terms of meeting the requirements, we are still far from being that. And the GBON, so Global Basic Observing Network, which I have mentioned just early on, is one mechanism by which we are going to improve the situation, hopefully in the next few years. So if you would compare that map with the map that has been shown previously by Dr. Kanawati and by Bruce of the CTBTO, you will see that there are some places where which are data sparse for WMO, and where we could make advantage of the infrastructure that has been deployed by CTBT. So I mentioned the unified policy for the international exchange of Earth system data. So it is about to be approved by Congress in a few months from now, hopefully. It is introducing the concept of core data, so those data that are necessary for the provision of services in support of protection and of life and property, and for the well-being of all nations, which are required to monitor and predict seamlessly and accurately weather, climate, water, and related environmental conditions. In parallel, we introduce a concept of recommended data, so where there are some less stringent requirements on our members to exchange the data. So this will be a very critical tool in the future for making Earth system data available to our prediction systems. Prediction and monitoring systems. So WMO, in terms of synergies, WMO, we can offer our infrastructure for data exchange, and we have also a so-called metadata repository, OSCAR, whereby you will find information on the observing stations. We have the WMO information system for the exchange of data, and if you want to make use of WMO infrastructure, there are some prerequisites, I would say. So, for example, there are some practices to be followed. You have to allocate a so-called WIGO station identifier for the station. You would have to nominate a focal point with whom we could discuss the technical details for the implementation of sharing data, for example. And you have to make use of the recommended data exchange formats that we use in WMO. In return, if partner organizations share data with WMO, they increase the visibility and the use of their data. They allow WMO to fill gaps, but also they will get information from WMO on the quality of these observations, because we have a pretty strong quality monitoring system in WMO. On the other hand, it can work both ways. You can use WMO infrastructure, but partner can also offer their infrastructure. Imagine, for example, to install ancillary sensors, meteorological sensors nearby or at CTBT stations, for example. So that's all I wanted to report. Thank you very much for your attention there, and I look forward to a successful discussion here in this panel. Thank you.
Great, thank you very much. And you've tried to make up time for us. That's appreciated. Next, if you can unshare your screen. Next is Steve McFeely with the UN Conference for Trade and Development Chief Statistician. If you could begin your presentation, Steve.
Great. Well, good morning, good afternoon, everybody, and thank you for the invitation to speak. You can see my screen. So, just begin, expert in hazard or disaster prevention or mitigation. My work and experience deals largely with economic data and analyses. But as Bruce mentioned at the start, I'm taking up a new role with the WHO next month, and many of the disasters that you're discussing have subsequent health implications. But of course, WHO is also interested in other crises, not least, as I'm sure you appreciate now, epidemics and pandemics. But despite my lack of expertise in this field,
Steve, can you make the projection larger, please?
Apologies.
Presentation mode, if you wish. Next one, the next one to the right. Thank you.
Is that okay?
That is perfect. Thank you.
Okay. So yeah, so I'd like to highlight just some issues from a statistical point of view that I think are still relevant to the discussion today, as they're more useful. So what I'd like to do is begin with a discussion just around some recent kind of statistics and their interaction with the COVID pandemic. So last year, the Global Health Security Index published their inaugural report, probably a bit unfortunate from their point of view in terms of timing. But they noted that countries were not prepared globally for catastrophic biological events. They weren't fully prepared for epidemics or pandemics. They noted that the collective international preparedness was weak, and many countries did not show evidence of health security capabilities. But prophetically, they said that knowing the risks was not enough. Political will was needed to protect people from the consequences of epidemics. And I think that this is very important when we get to the metrics piece. And they noted that unfortunately, political will for accelerating health security is caught in a perpetual cycle of panic and neglect. And I think that's probably relevant to a lot of what we're discussing. When something happens, there's panic. And then as soon as the crisis is over, we revert back to neglect. So they built this multidimensional index. I won't go through it except just to kind of show that they covered a range of kind of domains that you would expect a prevention index or an indicator like this to look at, including 85 sub-indicators. So quite a comprehensive metric. Now, I should note the Global Health Security Index was not designed specifically with pandemics in mind. It's a more broad index. But nevertheless, when we look after the first 6 months of the pandemic, what we see is, for example, in the US, which was ranked first as the country best prepared to deal with a biological crisis, but by kind of any metric of what you might call the worst affected countries. And the US was doing quite
You're breaking up, Steve.
badly. The same with the UK.
Steve, maybe you could turn off your video. Your sound is breaking up.
Is it still okay? Okay. Hang on. Let me just get my screen back.
You sound okay now.
Okay, can you hear me now? I'll
Your screen looks okay to us.
And then
Yes.
let me know if
Your audio is still going in and out.
okay. this raise questions. Obviously, in this was early days. Uh, the country ranking give a false sense of security countries.
Steve, we can barely hear you. Looks like he's going to try and log in again. Georgios, can you check your chat window?
Yeah, we have 4 minutes left. So I think we should come to concluding remarks soon, not immediately.
Okay. Maybe I could just say a few words, but Loretta has she gave the introductory talk before the panel started, and maybe she could just say a few words at the very end. I just say, in my presentation, I presented possible new sources of data. Indonesia presented definitely need for new data sources, and WMO indicated that they had a fair amount of infrastructure that could be shared, and then also their interest in sharing infrastructure resources, for instance, from CTBT. And then I think Steve's main point is something perhaps beyond our control is somehow to improve leadership in disaster situations. Loretta, do you want to? We just have a few 2 minutes left. Could you give us your thoughts? Unmute. Can you unmute yourself?
It's unmuted now. It didn't
Good.
allow me for. Yes. Well, thank you very much, Bruce. And I really enjoyed listening to all of these presentations. I think there were some very concrete ways in which CTBT could be joined up very specifically with WMO, but also with, as our colleague from Indonesia pointed out, so very concrete suggestions. It was a pity we missed that last presentation. I hope maybe the slides could be shared, because I think the point that was being made about political leadership is absolutely key. And it's not just around health emergencies or pandemics or epidemics, but definitely having better risk information, which of course monitoring systems provide, is only part of the equation. What's really important is how that information is used. And we have certainly seen in the case of the Palu, Indonesia earthquake tsunami situation that it's true, of course, that the information came too late. And it was a very quick early warning, that it was a very quick earthquake within 2 minutes. But we also know that had the population had better information on self-evacuation, if they had their own historical knowledge of the threats and the risks, that perhaps there also more lives could have been saved. And so we really do see a need for end-to-end early warning systems. And of course, better monitoring systems play nonetheless a very important role there. I would just maybe a final reflection is, of course, the work that you're doing in terms of collecting data and information on the nuclear issues is in itself a contribution to Sendai framework, as I pointed out, because the list of hazards that we have is broader than natural hazards. And so that is a very important role. And it's something that we at UNDRR perhaps do not emphasize enough. So I think from our side, we would be interested in seeing how we could perhaps better connect, further connect, and bring you into some of the work that we're doing with our science and technology groups as well, which are trying to advance the science agenda, and perhaps look at some of the linkages in particular around issues such as NATEC, where the nuclear aspect is linked to other types of natural hazards. So I think I'll leave it there, but thank you very much for the invitation and for the very good presentations. And I hope to receive the last one that we weren't able to hear, but it seemed to be very interesting. Thank you.
I think we'll be able to share. Yeah.
Yes, absolutely.
Sergio?
Here you can, you will be able to download it. From Vienna, thank you very much for participating in this very interesting panel. Thank you very much for the wonderful presentations, and we hope pretty soon we'll be able to discuss this in person. Thank you very much. Bruce, thank you very much for moderating.
Thanks everyone for attending. Right. Ciao.
Bye. Bye-bye.